Okay, this is going to be a very short video podcast. I just want to spend a few minutes on the pH scale. I don't want to belabor the point, but I do need for everyone to understand the pH scale because it's going to be so important to us in subsequent lessons. So let's start with the pH scale. Sorensen in the year 1805 or 1806 came up with this idea, and it was really ingenious because of the fact that it allowed individuals who weren't really familiar with logarithms or exponents or even hydrogen ion concentrations to speak about the relative acidity or basicity of certain compounds and other substances. And here's essentially how it works. It's really very simple. And that is that at the center of the scale is 7. Now that's neutral, and that's the most important number that we need to know because at the low end of the scale is 1. That's the most acidic. And 14 is the most basic on the upper right, on the right-hand side of the scale is 14. So it goes from 7 in the middle, 1 on the lower end, and 14 on the higher end, with the most acidic being 1 and the most basic being 14. Just a quick aside, you will occasionally run into acidities that are less than 1. You can have an acidity of 0. You can have a pH of a negative pH, but we won't often run into those. But I just wanted to tell you that just in case it does happen. And you can have pHs above 14. But let's take a look at some substances. I happen to have a few here. Let's start with water. This is distilled deionized water right here. This is water that has been had its impurities removed. And when I place a pH indicator, a pH sensor like the one that I have right here into the water, I know you can't see this, but I'll just tell you that the pH reading that it's giving me is very close to 7. It's 6. No, it's 7. So 7.00 is the pH of pure distilled deionized water, and certainly you should know that. Okay. I have a couple of other substances here. Let's take a 0.1 molar hydrochloric acid solution. And by the way, I'm just showing you this for so that you can compare acidities and basicities. Not that you need to memorize these or anything like that, but just so you can have some reference for comparison. This is a 0.1 molar hydrochloric acid solution, and I'm reading a pH of 1.00. 1.00 for 0.1 molar hydrochloric acid. So that would be at the low end. If I look at, here I have lemon juice, a little lemon juice. This one has a pH of 2.3, 2.4, 2.3, 2.3 for the pH of lemon juice, so quite acidic. Actually, I have some pure rainwater. We were in the middle of a drought, but it did rain a little bit, and I collected some rainwater, and the rainwater actually has a pH of 5.6. So it's not 7, it's a little bit below 7. So pure rainwater, 5.6 is the pH of pure rainwater, at least the pure rainwater that I collected. We're going to go to the positive end of the scale, or the basic end of the scale now. Let me just turn this on. This is ammonia. There we go. This is ammonia, and it has a pH of 11.2. So we're now on the right-hand side of the scale now. We're over here. 11.2 for ammonia. And let's see, one more. I have, this is a 0.1 molar sodium hydroxide solution. And when I place a probe into it, I get a pH of 13. 13 is the pH of the sodium hydroxide solution. That's a 0.1 molar solution. So these are substances that we find around our homes, and they fall all along this pH scale from 1 to 14. Now I want to talk just a little bit about what it means to go, say, from 1 to 2, 2 to 3, and so forth, because that can be a little bit misleading. Remember that this is a logarithmic scale. So if I go from 1 to 2, for example, from 1 to 2, that doesn't mean that I have half as many hydrogen ions. So remember, this is where on the left-hand side, this is a high concentration of hydrogen ions. This is a low concentration of hydrogen ions. But when I go from 1 to 2, it doesn't mean it gets twice as small. In other words, the hydrogen ion concentration gets twice as small. This is a logarithmic scale, and that, by the way, is log to the base 10. It's a logarithmic scale, not a ln to the base e, but a logarithmic scale to the base 10. That means as I move from pH 1 to pH 2, there are 10 times fewer, 10 times less hydrogen ions at a pH of 2 than there is at a pH of 1. If I go to pH equal to 3, and I want to compare then a compound or a substance that has a pH of 3 to one that has a pH of 1, the one that has a pH of 3 has 10 squared, because I've moved 2 units to the right, 10 squared, or 100 times fewer hydrogen ions. So from this lesson, I need you to know that. I need you to know that this is a logarithmic scale, and as I move from 1 to 2 to 3 and so forth, from left to right, I'm decreasing the hydrogen ion concentration by a factor of 10. I'm decreasing the hydrogen ion concentration by a factor of 10 each time. So do little problems, do little exercises in which you can say, you ask yourself, okay, if I go from a pH of 8 to a pH of 12, how many times fewer hydrogen ions are there? The next thing I need you to know from this lesson is that you can relate these pH values to hydrogen ion concentration. We'll, in our next lesson, take a look at some quantitative aspects of the pH scale. But before we do that, I simply need you to know this, that without a calculator, you should know that at pH equal 1, the concentration of hydrogen ions is 1 times 10 to the negative 1. So the concentration of hydrogen ions at pH 1 is 1 times 10 to the minus 1. The concentration of hydrogen ions at pH 7 is 1 times 10 to the negative 7. And the concentration of hydrogen ions at pH 14 is 1 times 10 to the negative 14. Okay? And so you can easily relate, if you know the pH, you can easily relate the hydrogen ion concentration. If, for example, you were told that the pH is equal to 3, then the concentration of hydrogen ions would be 1 times 10 to the minus 3. If the pH is equal to 12, then you know that the hydrogen ion concentration is 1 times 10 to the negative 12. And that's it. That's all that we need to know for now about the pH scale. So I'll see you on the next video podcast. Thank you.